Pi is a programmable large language model service system. It's open source, Apache 2.0 license. You can go to pi-project.org, check it out right now, right? I will basically take you a guided tour through Pi and how to use it. So our motivation developing Pi comes from dissatisfaction with existing inference engines such as vLLM, SGLang. So they evolve from an era like a large language model used for chatbots, right? So basically, all of them support the chat API. You send a prompt and you get a response from the large language model. In a way, you could argue this inference engine basically treat large language model as a locked up oracle, right? In the jail, have access to nothing else, right? You have slipped into a question and the oracle answers your question in response. It's amazing today all the agentic application built on top of this jail locked up oracle model. So we really want to liberate the oracle out of the jail and tap into the full power intelligence of large language models. So agentic applications are no longer chatbots. They're programs, right? They use memory. They use tools. They fork, they branch, they yield, they block, right? In all aspects, they are programs, right? They could also use different custom reasoning logic, depends on what question you're asking, what tasks you're involved. You could use graph sorts, you could bin search, you could use constraint decoding, and you could use any one of these test time scaling tricks people are talking about these days to get more intelligence out of the same model. Today, the prompt serving inference engine are ill-suited for agentic applications because the inference engine hide behind the chat API, and the KV cache, which is very resource intensive, is invisible to the application. Tool calls often involve network round trip, right? Tool calls use have to come back to the agents and results and sent back to the inference engine for further processing. I'll show you an example later about this problem. And if you would like to use any custom decoding strategy to test time scaling, you have to modify the engine. You have to invasively modify the engine. So as a result, your agent application uses more tokens, suffer from a longer latency, and more importantly, you lose control of the inference engine. Any ideas you would like to use to make the inference process faster, you rely on the inference engine to implement them, and you basically lose your IP to the inference engine. The inference engine owns all the optimization, right? For example, prefix caching, radix attention, these are all IPs owned by the inference engine. There's no way agent application could own the optimization for inference process. So the goal of a Pi is basically to change this from model serving system from serving prompt to serve program, right? We'd like to treat large language model like a CPU. And agentic application basically can write small program that control how the CPU works. And therefore, you could implement using the CPU and use a small program, you can implement application-specific optimization. You could control the model inference process, control the KV cache, control the decoding stage. And you don't have to modify the inference engine at all, okay? So here is how Pi changed the serving system, right? On one side, you have the old school inference engine, basically is chat API, agents you send a prompt to inference engine, receive a response. With Pi, the agents still use chat API, send the prompt, but agents can also send a small program called infinet to run inside the serving system and to control the inference process for efficiency and low latency. Okay, infinet is this program, right? It controls the inference flow, and Pi natively support Rust. We do write infinet Rust. We can also support Python, TypeScript, and infinets are compiled and into WASM and executed with WASM runtime. Okay, and we provide SDK for you to write infinets, and we also provide the toolchain called Bakery that for dispute and develop infinite. So with the infinite, the Pi runtime expose the API so that infinites can do token level forward pass control, right? You could easily implement any constraint decoding, any speculative decoding, custom sampler, etc. Right? You could do fine-grained KV cache control, right? U means the agent, right? You could control it using infinite. And you can implement prefix caching, which is blindly supported by vLLM, SGLang. You could also support a fork, efficient fork branch, and the best of tree of sorts, etc., more efficiently by reusing KV cache between branches, and in a deterministic manner, right? In comparison, in vLLM and SGLang existing inference engine, their KV cache reuse is best ever, right? So they treat each prompt as independent request and try to see if there's a prefix matching, you can reuse the KV cache. In Pi, things become deterministic, and the agents can use infinites to basically fix the KV cache needs in the memory and reuse across different branches. And infinites can also use tool directly. So therefore, you do not have to go back to clients, right? You do a function call, MCP, virtual file system. We have embedded language runtime there too. So that saves a lot of round trip time between agents and inference system, improve latency. And the open source version, the source code already included a large number of infinites that is ready to use, ready to deploy. You can use to, when you are serving a prompt, you can, based on what prompt it is, you can pick the right infinites to either improve the speed or improve the quality of inference, which I'll give two examples later on. Check out, it's in the Pi project. There is a folder where all the example infinites are described. And the Pi engine is the other part of Pi. It's basically the operating system to run infinites, right? If you view infinites agent provide a small program running the serving system, the Pi engine, essentially the operating system, have two parts. As a runtime, is written completely in Rust, which we'll talk a little bit more later. Basically, host the WASM runtime and schedule the infinites and manage the KV cache globally, and also has a market-based contention manager inside the system for resource management. And we also support the WebSocket protocol in this runtime. And then the other part of this OS is the drivers, which is model-facing part of it. Currently, we native speak CUDA driver and a local driver for CPU and Apple Silicon. And we also have experimental support for vLLM, SGLang. Basically, we treat them as token generators, right? We can, Pi can sit on top of them, therefore support all the models that they support. So let's look inside the runtime, right? And see how Pi is different from existing inference engines. Existing inference engine like vLLM, SGLang is implement basically a global autoregressive loop, right? So a prompt come in, you embed, you prefill, you decode, and then sample, and you come back, right? And then you batch multiple prompts. And once you send the prompt goes through this loop, right, automatically. And the agentic application has no control about this loop, right? It's stopped by its own. In contrast, the Pi's runtime disaggregate this loop into small handlers, right? And basically, the agentic application submit the infinite as a program. This program make calls into the handlers, and the control layer of Pi basically aggregates this handler calls and schedule them accordingly. So this adds the flexibility about the agentic application. Infinites could do any arbitrary program. So the infinites can go do things beyond the autoregressive loop. In a way, autoregressive loop, the current inference engine, can be implemented as a while loop in infinite, right? So, but infinites allow you to implement other weird things, optimizations, right? Okay. So let's look into how Pi make agent application better, right? So this is one example of a tool using. Pi basically, with infinite, allow you to do in-server tool use. On my right side, that's how vLLM SGLang handle tool use, right? So the agent will send the prompt, and the serving system use a model and will figure out, okay, to serve this prompt, we need to use a tool, for example, Google search. Then the tool use will become a response, send it back to the agent, and agent will then go search Google, right, the Google search, and get the results, append the result to the prompt, and resend the prompt back to the serving system, and so on and so forth. And although the vLLM SGLang both implement prefix caching, therefore, in theory, these prompts you send to the serving system, since they share much of its prefix, therefore you can reuse the KV cache. But such KV cache reuse is best effort is not guaranteed, right? When the system is under stress, the KV cache, the prefix cache could get kicked out of memory, and you end up having to recompute the prompt again and again. On my left side would be how Pi implement tool use, right? Tool use would be implement as part of infinet, and the agent will only send the prompt along with the infinet to run inside the serving system. And when the large language model come back to tell the agent you need to use Google search, the Google search will be performed by infinet itself within the server without leaving the serving system. And a single inference process is involved instead of, unlike in vLLM SGLang's case, you have to turn this process into a multiple rounds of conversation. In this way, Pi leads to lower latency, higher throughput, and using fewer tokens, right? So here's some quantitative results, right? We compare Pi with vLLM SGLang, and we can improve both latency and throughput by up to 1.5 times. This is not all, right? The most valuable thing about Pi is we allow the application to use its own knowledge about the application to do custom application-specific optimization. For example, the agent application knows some tools will use more often than others. Therefore, I could implement infinites in a way that I can give the KV cache for these more frequently used tools higher priority in the cache, right? And if I know some tools are fine and forget, so I could, in the infinite, I could concurrently call these tools without waiting for the results to come back. And if I know some tools are only used once, then in the infinites, I could optimize the system to drop the KV cache of this one-time use tool once it's used, right? So therefore, lead to way much more efficient resource usage. So, and this optimization can be compounded, right, on the results. And we basically can achieve more than 3 times higher throughput than vLLM. And the benefits grows when the system is under stress, right? The load of the system increase. And in vLLM, because the prefix caching is the best effort, so there's no guarantee. So therefore, when the system is under stress, your effectiveness of prefix caching become lower. But in Pi, the prefix caching, the KV cache reuse is the semantics of infinite is deterministic. Okay, here's a demo, right? Let me show. Here is I run Pi, and I have on my right side is a baseline, basically. On the right side is, on the left side is use speculative decoding, right? So this is basically for this particular request, this is a Q1.6b model running Pi, and basically asked to replace the keyword total into subtotal in a Python program, right? You can on the left. It's just no speculative coding, slow, things come out slowly, one. On the right, we actually enabled speculation, use a very simple speculation execution, so therefore things come about much faster. And in this case, for us to see the demo, I actually delayed the token generation, right? So without the delay, the token per second is actually 4 times higher with speculative execution. And this is a command line choice for each prompt. instead of engine modification. This is a difference. In vLLM, for you to implement speculative decoding, you have hacked the engine, and the speculative decoding have to be applied to everybody, every request. Same algorithm will be applied to every request. In Pi, for different requests, for this, you could use different algorithm. For example, for this keyword replacement, a very simple speculative decoding approach will be effective, and we use it. Another second example is I show how Pi could use test time scaling, use test time tool used to improve the quality of inference, right? Again, the baseline is still same model 0.6b, and basically we ask math question as to solve. You can see it get the answer wrong, right? Because it's not a big model. But with Pi, we can implement a verifier, right, inside infinets. And when verifier find the answer is not correct, you can basically prompt the model to regenerate again. So in this case, you get a correct answer, only at the moderately increase of computation. So Pi basically allow you to apply arbitrary application per request. Any request to the model, you could pick a different optimization in the form of infinite. Okay? So I encourage you to try it out. You go to the web page, and if you click Get Started, and there's a walkthrough, and you can try it on your laptop. If you're on Linux and Mac, it's very simple. Just 3 lines of code. You actually could start playing with the model. Right, I welcome you guys to contribute to develop Pi further, and open source contribution. Or if you're interested in PhD, we're recruiting for PhD students to work on Pi-related project. And if you're looking for a job, we have engineer positions at List AI, who is a Pi-focused startup right now. If you go to Pi webpage, go to GitHub repository, give us a star. I appreciate that. Thank you.